Lecture 9.4, Radius of Convergence. This is Abraham Lincoln's house in Springfield, Illinois. This is the house where Abraham Lincoln lived when he was a lawyer and where he waited to hear if he had been elected president. The series that are of the most interest to us are those that converge. Today we will consider the question, does this series converge, and if so, for what values of x does it converge? The first requirement of convergence is that the terms must approach zero. The nth term test for divergence. The summation from n equals 1 to infinity of a sub n diverges if the limit as n approaches infinity, a sub n, fails to exist or is not zero. Note that this can prove that a series diverges, but cannot prove that a series converges. Example, the summation of n equals 0 to infinity, n factorial, x to the n. If the absolute value of x is greater than 1, then n factorial x to the n grows without bound. If the absolute value of x is between 0 and 1, then the limit as n approaches infinity, n factorial x to the n, equals the limit as n approaches infinity, n factorial divided by 1 over x to the n equals infinity. We know this because as n approaches infinity, eventually n is larger than 1 over x, therefore the numerator grows faster than the denominator. Therefore, the series diverges, except when x equals 0. There are three possibilities for power series convergence. 1. The series converges over some finite interval, the interval of convergence. There's a positive number r such that the series diverges for the absolute value of x minus a is greater than r, but converges for the absolute value of x minus a is less than r. The series may or may not converge at the endpoints of the interval. 2. The series converges for every x, that is, r equals infinity. Or 3, the series converges at x equals a and diverges everywhere else, r equals 0, as in the previous example. The number r is the radius of convergence. The direct comparison test. For non-negative series, if every term of a series is less than the corresponding term of a convergent series, then both series converge. In this illustration, if the upper series, represented by the red dots, converges, and every term in the lower series, represented by the blue dots, is less than the corresponding term in the upper series, then this series must also converge. If every term of a series is greater than the corresponding term of a divergent series, then both series diverge. So if the lower series in this case diverges, then the upper series, represented by the blue dots, must also diverge. So in the second case, our blue series is pushed up to infinity. In the first case, the blue series is bounded above by the red series and can't go up any further. Example, prove that the summation from n equals 0 to infinity of x to the 2n over n factorial squared converges for all real x. There are no negative terms, and x to the 2n over n factorial squared is less than or equal to x squared to the n over n factorial. In this case, the numerators are the same, and the denominator on the left side is larger than the denominator on the right side, making it a smaller fraction. The summation from n equals 0 to infinity of x squared to the n over n factorial is the Taylor series for e to the x squared, which converges. Therefore, the original series must converge. The direct comparison test only works when the terms are non-negative. I might mention this example is a good argument for knowing your formulas, because it really helped to recognize this series as the Taylor series for e to the x squared. Absolute convergence. If the summation of the absolute values of the terms converges, then we say that the summation of a sub n converges absolutely. The term converges absolutely means that the series formed by taking the absolute values of each term converges. Sometimes in the English language, we use the word absolutely to mean really or actually. This is not the case here. If the summation of the absolute value of a sub n converges, then the summation of a sub n converges. In other words, if the series formed by taking the absolute value of each term converges, then the original series must also converge. If a series converges absolutely, then it converges. Example, the summation from n equals 0 to infinity of sine x to the n over n factorial. We test for absolute convergence. We notice that the original series is sometimes positive and sometimes negative. The absolute value of sine x to the n over n factorial is less than or equal to 1 over n factorial, because the maximum value of the absolute value of sine x is 1, the minimum value of the absolute value of sine x is 0. Since e to the x equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial through x to the n over n factorial, the summation from n equals 0 to infinity of 1 over n factorial converges to e to the 1, or e. Therefore, the summation from n equals 0 to infinity of the absolute value of sine x to the n over n factorial converges by the direct comparison test. Since the summation from n equals 0 to infinity of sine x to the n over n factorial converges absolutely, it converges. The ratio technique, and this is one of my favorites. We have learned that the partial sum of a geometric series is given by S sub n equals t sub 1 times 1 minus r to the n over 1 minus r, where r equals the common ratio between terms. When the absolute value of r is less than 1, the series converges, because when the absolute value of r is less than 1, this term disappears. Geometric series have a constant ratio between terms. Other series have ratios that are not constant. If the absolute value of the limit of the ratio between consecutive terms is less than 1, then the series will converge. For the summation from n equals 1 to infinity of t sub n, if L equals the limit as n approaches infinity of the absolute value of t sub n plus 1 over t sub n, then if L is less than 1, the series converges. If L is greater than 1, the series diverges. And if L is equal to 1, the series may or may not converge. We say that it is inconclusive. Example: the natural log of 1 plus x equals x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4, and so forth. If we replace x with x minus 1, we get ln x equals x minus 1 minus 1/2 x minus 1 squared plus 1/3 x minus 1 cubed minus 1/4 x minus 1 to the 4th, etc., which is equal to the summation from n equals 1 to infinity of negative 1 to the n plus 1 times 1 over n times x minus 1 to the n. We evaluate the limit as n goes to infinity of the next term, which would be negative 1 to the n plus 2 times x minus 1 to the n plus 1 over n plus 1. So to find the next term, we replaced n with n plus 1 wherever it occurred. And then we want to divide by the general term, but to divide a fraction, we flip it over and multiply. So we have a sub n plus 1 over a sub n, which is the same as a sub n plus 1 times 1 over a sub n. In this case, we can cross out the negative 1s. They're an absolute value sign, so it doesn't matter whether it's positive or negative. Then we expand x minus 1 to the n plus 1 to be x minus 1 to the n times x minus 1. Now we can cancel x minus 1 to the n, giving us the limit as n goes to infinity, x minus 1 times n over n plus 1. as n goes to infinity, this 1 becomes insignificant, and so we have n over n, which can cancel, and we're left with the absolute value of x minus 1. If the limit of the ratio between consecutive terms is less than 1, then the series will converge. So this series should converge if the absolute value of x minus 1 is less than 1, which could be rewritten as negative 1 is less than x minus 1 is less than 1. Adding 1, we get 0 is less than x, which is less than 2. So the series converges over the interval from 0 to 2, but we should check the endpoints. At x equals 0, we have ln of 0 equals 0 minus 1 minus 1/2 times 0 minus 1 squared plus 1/3 times 0 minus 1 cubed minus 1/4 times 0 minus 1 to the 4th, which is negative 1 minus 1/2 times negative 1 squared plus 1/3 times negative 1 cubed minus 1/4 times negative 1 to the 4th, or negative 1 minus 1/2 minus 1/3 minus 1/4. We recognize this as a negative harmonic series which diverges, which we would expect since the natural log of 0 is undefined and the limit as n approaches 0 from the right-hand side of ln of n equals negative infinity, and our series is approaching negative infinity. At x equals 2, we have ln2 equals 2 minus 1 minus 1/2 times 2 minus 1 squared plus 1/3 times 2 minus 1 cubed minus 1/4 times 2 minus 1 to the 4th, which is 1 minus 1/2 plus 1/3 minus 1/4. We recognize this as the alternating harmonic series, which converges, and apparently it converges to the natural log of 2. Therefore, the interval of convergence is from 0 to 2. It's open on the left and closed on the right. The radius of convergence is 1. Another example, the summation from n equals 1 to infinity of n over 3 to the n times x minus 5 to the n, which is 1/3 times x minus 5 plus 2/9 times x minus 5 squared plus 3/27 times x minus 5 cubed. Applying the ratio test, we have the limit as n approaches infinity of the absolute value of n plus 1 times x minus 5 to the n plus 1 over 3 to the n plus 1. Here we've replaced n in the general term with n plus 1. We multiply times the reciprocal of the general term, which is 3 to the n over n times x minus 5 to the n. Now, before we can cancel, we have to expand some terms. We expand x minus 5 to the n plus 1 to x minus 5 to the n times x minus 5. And we expand 3 to the n plus 1 to 3 to the n times 3. Now we can cancel x minus 5 to the n and cancel 3 to the n, giving us the limit as n approaches infinity of the absolute value of n plus 1 times x minus 5 over 3n. We can factor out the x minus 5 because there's no n in that term, so the limit doesn't affect it, and we get L equals the absolute value of x minus 5 times the limit as n approaches infinity of n plus 1 over 3n, which becomes L equals the absolute value of x minus 5 times 1/3, because as n approaches infinity, this 1 becomes insignificant, and so we can cancel the n's. So to converge, we must have 1/3 times the absolute value of x minus 5 less than 1, or the absolute value of x minus 5 less than 3, which we can rewrite as -3 is less than x minus 5, which is less than 3, or 2 is less than x, which is less than 8. So the interval of convergence is the interval from 2 to 8, and the radius of convergence is 8 minus 2 over 2, or 3. Now in this case, we're going to skip over checking the endpoints since we were mostly looking for the radius of convergence. Another example, the summation as n goes from 1 to infinity of n factorial over n to the 4th times x minus 3 to the n. We can expand this and then apply the ratio test. L equals the limit as n approaches infinity of the absolute value of n plus 1 factorial times x minus 3 to the n plus 1 over n plus 1 to the 4th times n to the 4th over n factorial times x minus 3 to the n. Before we can cancel, we need to expand several terms. In particular, note that n plus 1 factorial becomes n factorial times n plus 1. The exponential terms expand the same way the terms did in the last example. Now we can cancel n factorial and x minus 3 to the n. The x minus 3 factors out of the limit because it does not contain an n, and we get the absolute value of x minus 3 equals the limit as n goes to infinity of n minus 1 times n over n plus 1 to the 4th. As n approaches infinity, the 1 in the denominator becomes insignificant, and n over n plus 1 approaches 1. But we still have an n plus 1 in the absolute value signs. So L equals infinity for all x not equal to 3, because as n approaches infinity, the limit approaches infinity. The radius of convergence is 0. At x equals 3, the series is 0 plus 0 plus 0, which converges to 0. Note, if r is infinite, then the series converges for all values of x. except in this case, x equals 3. Another series for which it is easy to find the sum is the telescoping series. For example, the summation as n goes from 1 to infinity of 1 over n times n plus 1. Using partial fractions, we have 1 over n times n plus 1 equals a over n plus b over n plus 1. Multiplying through by the common denominator, we get 1 equals a times n plus 1 plus b times n. Clearing the parentheses, we have 1 equals an plus a plus bn. So 1 must equal a, and 0 must equal a plus b. Therefore, 0 equals 1 plus b, or negative 1 equals b. Now we can rewrite our series as a summation from n equals 1 to infinity of 1 over n minus 1 over n plus 1. Generating the first few terms, we get 1 minus 1/2 plus 1/2 minus 1/3 plus 1/3 minus 1/4, and so forth. But we notice that parts of the terms cancel. We can cancel a negative 1/2 and a positive 1/2, and a negative 1/3 and a positive 1/3. And so the third partial sum is 1 minus 1/4. The nth partial sum would be 1 minus 1 over n plus 1, because we could just keep canceling. If we take the limit as n goes to infinity, we see that the sum of the infinite series in this case is just 1. For a telescoping series, the summation from n equals 1 to infinity of b sub n minus b sub n plus 1 converges to b sub 1 minus the limit as n goes to infinity of b sub n plus 1.